This video is part of the course Forensic Physics, How Science Solves Crimes in Court. In this course, we examine how the laws of physics are applied to real-world crime and accident scenes, and how scientific reasoning supports legal decision-making. Each episode focuses on a specific physical principle and shows how it constrains what could, and could not, have happened. This educational initiative is presented by the Physical Sciences Consultorium, a platform dedicated to explaining science with clarity, rigor, and real-world relevance, especially where science intersects with law and society. Accidents are among the most common events investigated in courts. They are also among the most misunderstood. Eyewitnesses often disagree. Memories conflict, and narratives compete. Yet accidents are not random stories. They are physical events governed by motion. Every vehicle involved obeys the same laws of physics. No exception is made for intent or testimony. Forensic physics treats accidents as problems of reconstruction. The goal is not to assign blame, but to constrain reality. At an accident scene, motion has already ended. Vehicles are at rest. But traces remain. Those traces record what happened during motion. Skid marks on the road, vehicle deformation, and final resting positions all carry information. Physics provides the language to interpret that information. The central question is simple. Can motion be reconstructed after it has stopped? Physics answers yes, within limits. Accident reconstruction begins with kinematics. Kinematics describes motion without asking why it occurred. It focuses on speed, distance, time, and direction. These quantities leave measurable traces. One of the most common traces is the skid mark. Skid marks form when tires lose rolling traction and slide. The length of a skid mark is not arbitrary. It is linked to the vehicle's speed before braking. Longer skid marks generally indicate higher speeds. Shorter skid marks indicate lower speeds. However, skid length alone is not enough. Road conditions matter. Dry asphalt, wet roads, gravel, and concrete all have different friction properties. Physics accounts for this using coefficients of friction. These coefficients are measured experimentally. They are not guessed. Using friction estimates, investigators can constrain speed ranges. They do not calculate a single value. Reaction time is also important. Before braking begins, drivers continue moving. This reaction distance adds to stopping distance. It cannot be ignored. Human reaction times vary. Physics therefore works with realistic ranges. This immediately shows a key principle. Accident reconstruction never produces exact numbers. It produces constrained possibilities. Eyewitnesses often estimate speed poorly. Physics consistently outperforms intuition in this regard. At this point, an important clarification is needed. Speed before braking is not the same as speed at impact. Braking may reduce speed significantly. In some cases, braking never occurs. Reconstruction must therefore consider the entire sequence. From perception to reaction to braking to impact. Kinematics allows investigators to map this sequence. It connects distances to changes in speed. Once vehicles collide, momentum becomes central. Momentum describes motion during impact. Unlike speed, momentum is conserved during collisions. This makes it a powerful forensic tool. When two vehicles collide, their motions change abruptly. Yet total momentum is conserved. This principle allows investigators to reconstruct directions of motion. It is especially useful in multi-vehicle accidents. After impact, Vehicles may rotate, slide, or separate. These motions are not random. They follow momentum transfer rules. Mass and velocity both matter. Importantly, a heavier vehicle does not automatically dominate. Direction and speed play critical roles. This often surprises non-specialists. Physics clarifies misconceptions. Momentum analysis does not require knowing driver intent. It requires only measurable physical quantities. At this stage, accident reconstruction shifts from kinematics to dynamics. Forces and energy begin to matter. However, energy analysis must be handled carefully. Damage alone does not determine speed. Vehicle deformation reflects energy absorption. But materials behave differently. Crumple zones are designed to absorb energy. They protect occupants by deforming. This means that visible damage does not scale linearly with speed. More damage does not always mean higher speed. Forensic physics therefore combines methods. No single indicator is sufficient. Speed estimates from skid marks are combined with momentum analysis. Damage patterns provide supporting evidence. This multi-layered approach is essential. Over-reliance on one method leads to error. Environmental factors also matter. Road slope, weather, and vehicle condition influence outcomes. Tire condition affects braking. Weather affects friction. Road geometry influences vehicle paths. These factors must be documented. Forensic physics does not eliminate uncertainty. It manages it. Every reconstruction includes assumptions. These assumptions are stated explicitly. If assumptions change, results change. This transparency is essential in court. Courts rely on accident reconstruction to test narratives. Physics constrains what is plausible. If a claimed speed contradicts physical limits, the claim fails regardless of testimony. At the same time, physics does not assign guilt. It defines boundaries. Accident reconstruction is powerful, but it is not infallible. Forensic physics must always acknowledge its limits. Road friction is rarely uniform. It can vary across short distances. Weather changes friction rapidly. Rain, dust, and oil alter braking behavior. Tire condition also matters. Worn tires behave differently from new ones. Vehicle mass is usually known accurately. But load distribution may not be. Passengers, cargo, and fuel affect inertia. These factors are sometimes estimated. Measurement error is unavoidable. Skid lengths are measured after the event. Marks may be incomplete or obscured. Some evidence may be lost. Reaction time introduces further uncertainty. Human response varies widely. Physics cannot assign a single reaction time. It must work with realistic ranges. Because of these uncertainties, reconstructions always produce intervals. They do not yield exact speeds or forces. This point is often misunderstood. Uncertainty does not mean unreliability. It reflects honest scientific practice. It prevents false precision. Popular media often portrays reconstructions as exact. Computer animations appear definitive. In reality, reconstructions explore possibilities. They test whether claims are physically plausible. This distinction is critical in court. Judges and juries must understand it. Forensic physicists therefore emphasize explanation over calculation. They prioritize clarity. Equations are rarely shown in court. Diagrams are far more effective. Scaled diagrams show distances and directions. They make assumptions visible. Animations are used carefully. They represent one consistent scenario, not the only one. Experts must explain that alternatives may exist. The goal is constraint, not certainty. Cross-examination often targets assumptions. This is expected and appropriate. A well-prepared expert welcomes such questions. Physics is strongest when transparent. Accident reconstruction does not decide guilt. It evaluates physical possibility. If a driver claims an impossible maneuver, physics rejects the claim. If multiple scenarios are physically plausible, physics cannot choose between them. This neutrality protects justice. It prevents science from becoming advocacy. Forensic physics serves the court, not a side. Its loyalty is to natural law. This episode has shown how motion, momentum, and energy shape accidents. It has also shown why reconstructions must be cautious. Physics constrains narratives. It does not replace legal judgment. Understanding this balance is essential. It distinguishes real forensic science from spectacle. This course is presented by the Physical Sciences Consultorium. PSC is committed to rigorous, responsible science communication. The aim is to build understanding where science meets law. Not to dramatize, but to clarify. If you find this course valuable, please like this video and share it with students and educators. Subscribing to the channel supports future episodes and allows PSC to continue producing open access educational content. In the next episode, we turn to sound and signals. We explore how acoustics and physics are used in forensic investigations. From gunshot localization to audio analysis, physics once again constrains reality.